Okay, so we move on in Chapter 13 now to apply some of those previously learned skills of calculating concentrations, and we apply them to colligative properties. So if we think about colligative properties, there's really 4 colligative properties that we talked about. We talked about vapor pressure lowering, boiling point elevation, and these two are related. We talked about freezing point depression, and then we talked about effects on osmotic pressure. So this first problem has to do with vapor pressure lowering. And the problem asks to find the vapor pressure lowering, defined as delta P. And one thing to think about is we learned about 2 different equations that we can use with regards to vapor pressure. The one is vapor pressure lowering, and that's this equation. The vapor pressure lowering is equal to the mole fraction of the solute times the vapor pressure of the pure solvent. And that's the equation that we'll be using today. Again, the other equation, I'll just write it down here so we have it, has to do what the absolute vapor pressure is of the solution as a function of the mole fraction of the solvent times the vapor pressure of the pure solvent. And again, one of the things to note that's different is this side uses mole fraction solute, this side uses mole fraction solvent. Remembering that mole fractions go between 0 and 1, we can kind of make sense out of these equations. That if we have pure solvent, the mole fraction of solvent will be 1. 1 then times this value is still this value. So the vapor pressure of the solution really hasn't changed because we haven't added anything to it. So this is really, the mole fraction is really going to represent a scaling factor. As we add more solute, the mole fraction solvent is going to decrease. And so that's going to scale down the vapor pressure or lower the vapor pressure of the pure solvent, and that will be reflected in a lowered vapor pressure of the solution. The equation on the left here, because we're using mole fraction of solute, again, if we have a pure solvent solution, the mole fraction of solute is 0. And so 0 times this value is 0, and that makes sense because the change in the vapor pressure lowering, will be 0 if there's no solute present. So really this value will get larger and larger then as the mole fraction solute becomes more significant. You could actually solve this problem using either of these equations. It's a little bit more straightforward using the equation that actually starts with vapor pressure lowering. But again, if you use this one, and you find out what the vapor pressure is of the new solution, you'd have to take the difference of these 2 values to figure out what the change is, the vapor pressure lowering. Okay, so that being said, let's start this problem. This problem tells us that we make a solution by mixing 10 milliliters of glycerol to 500 milliliters of water at 50 degrees C. They tell us that at this temperature, the vapor pressure of water is 92.5 torr, and its density is just less than 1. They also provide the density of glycerol at 1.26 grams per milliliter. Now you might ask, why are they providing us with 2 densities? Sometimes problems might provide information that's kind of extraneous. I try not to have problems where you do that, where there's information there that you don't need, that kind of is just there to trick you or mislead you. But in this case, we're given, if we again want to calculate the change in vapor pressure, the vapor pressure lowering, we're actually given directly the vapor pressure of the pure solvent. This is given at 92.5 torr. So this is the only piece of information that we need to find. But if we kind of define what this is, the mole fraction of solute, which in this case is glycerol, is going to be the moles of glycerol over the moles of glycerol plus moles of water. We're given volumes of glycerol and we're given volumes of water. So we're given volumes of a material. That's information that we know, and where we want to go is moles of material. Now, there's no direct relationship between volume and moles that we have here. A direct relationship is actually molarity, but we're not given a molarity of solution. We are, however, given a density. Density allows us to relate volume to mass, right? Density equals mass over volume. And then we can go between mass and moles using molecular weight, because molecular weight is grams per mole. So I call these walk-betweens. So when you're doing unit conversion or dimensional analysis, you can walk between information that's given, information that you know, to get to information that you want to know. So for this problem, since we are given volumes of both our materials, and we know what the materials are, they give us the molecular weight for glycerol, we can easily convert volume to mass using density, and then mass to moles using molecular weight. So let's go ahead and do that here. So we've got 10 milliliters of glycerol times the density of glycerol. 1 milliliter of glycerol is 1.26 grams. And again, having units here is really important to make sure that we put the 1.26 on top here with its correct unit grams, and 1 milliliter goes on the bottom there. If you inverted this, you'd have a slightly incorrect answer. 92.09 grams of glycerol for 1 mole of glycerol, and that's 0.137 moles of glycerol. Let's go through the same calculation for water. 500 milliliters of water, and that's 0.988 grams of water over 1 milliliter. And notice again, the density of water is not always 1 gram per milliliter. At 50 degrees, it's slightly less than that. And 1 mole of water is 18.02 grams. So that's 27.4 moles of water. All right, so plugging that into mole fraction. So mole fraction of our solute, which is again our glycerol, is 0.137 moles over 0.137 moles plus 27.4 moles, and we get 0.00498. Remember, mole fractions again are unitless. I would not round this number early on here. We want to keep as many significant digits as possible until we get to our final answer. Vapor pressure lowering is thus then equal to the mole fraction of our glycerol here times the vapor pressure of water at that temperature. So it's 0.00498 times 92.5 torr, and we get to 0.461 torr. So this tells us that our vapor pressure has been lowered by about a half a degree. So, or a half a torr, excuse me. So the vapor pressure is going to be about 92. So keep in mind, if the problem asked what is the vapor pressure of the solution, we would need to take the difference here. So the vapor pressure of the solution we'd need to have as the vapor pressure of the pure solvent minus whatever that delta P is. So in that case, we'd get to something that's about 92 torr. Alternatively, if you wanted, you could start the problem using this equation to start out with. Again, now it's going to be the mole fraction of our solvent, which is water. So we're going to have quite a large number here, because this is going to be 27.4 up here. Quite a large number that we have here means that we're going to be just scaling this down a little bit. When I say quite a large number, I mean fairly close to 1. So we're barely scaling this down a little bit to have our solution. So it will again be close to 92 torr.